the unit of thermodynamics, in previous lecture we discussed some examples related to different types of processes, work, pressure volume work, internal energy, zeroth law of thermodynamics and first law of thermodynamics. In continuation, today we are going to discuss some examples related to first law of thermodynamics, some special forms of first law of thermodynamics, exact and inexact differentials, enthalpy of a system and relationship between delta H and delta E. Let us start with some examples related to first law of thermodynamics. Here is first example. A system is provided 50 joules of heat and work done on the system is 10 joule. What is the change in the internal energy? As Q is 50 joules and W is 10 joules, it is plus 10 joules because it is work done on the system. Delta U is equal to Q plus W, as you know from first law of thermodynamics. Therefore, delta U will be equal to 50 plus 10, that is 60 joules. There is another example to understand the sign conventions of heat and work. Here it is. The work done by a system is 8 joules when 40 joules of heat is supplied to it. Calculate the change in internal energy of the system. Here work is done by the system, hence it will be minus 8 joules, and heat is absorbed by the system, hence it will be plus 40 joules. According to first law of thermodynamics, delta U or delta E is equal to Q plus W. Therefore, delta U equal to 40 minus 8 joules, that is 32 joules. Let us practice another example related to first law of thermodynamics. If 500 calories of heat energy are added to a system and the system does 350 calorie of work on the surroundings, what is the energy change of the system? Heat absorbed by the system will be equal to plus 500 calories and work done by the system will be equal to minus 350 calories. According to first law of thermodynamics, delta E or delta U is equal to Q plus W. Therefore, it is equal to 500 minus 350, that is 150 calories. First law of thermodynamics can take special forms in some different conditions. Let us discuss these special forms of first law of thermodynamics. For a cyclic process, if it is isothermal, delta E will be equal to 0, and according to first law of thermodynamics, delta E or delta U is equal to Q plus W. Therefore, if delta E is equal to 0, Q will be equal to minus W. For an isochoric process, volume will remain constant. Therefore, delta V will be equal to 0, or we can say that work done by the system or work done on the system will be equal to 0. Therefore, W will be equal to 0. Hence, the first law of thermodynamics, that is delta E equal to Q plus W, will take the form delta E equal to Q. Therefore, Q at constant volume will be equal to change in internal energy of the system. For an adiabatic process, heat transferred to the system or from the system is equal to 0, that is Q is equal to 0. Therefore, putting the value of Q equal to 0 in the expression for first law of thermodynamics, we will get delta E or delta U equal to W. For an isobaric process, pressure remains constant. Hence, for the expression of first law of thermodynamics, that is delta E equal to Q plus W, we can put W equal to minus P delta V, and we will get the expression as delta E equal to Q minus P delta V. Now we are going to discuss exact and inexact differentials. As you know that delta U equal to Q plus W, as delta U is a definite quantity and Q is not a state function, hence W is also not a state function. Mathematically, it can also be said that internal energy is an exact differential, but work and heat are not exact differentials, or we can say that work and heat are inexact differentials. Exact differentials can be integrated between the proper limits, but inexact differentials cannot be integrated. We can say that du is an exact differential, hence integration of du between the limits u1 and u2 will be equal to u2 minus u1. But work done or heat exchanged are inexact differentials, hence integration of work done, that is dw, between the limits w1 and w2 will not be equal to w2 minus w1, or integration of q between the limits q1 and q2 will also not be equal to q2 minus q1. Enthalpy of a system is another very important property for thermodynamics. At constant volume, as system does not do any pressure volume work, hence delta U is only equal to delta H. But at constant pressure, system also does work in expansion, that is, system expends some energy during the work of pressure volume. Hence, the heat content of the system at constant pressure is equal to the internal energy change of the system plus pressure volume energy, that is work of expansion or work of contraction. This heat at constant pressure is termed as enthalpy. Mathematically, enthalpy is presented as H equal to E plus PV or U plus PV, as internal energy has a symbol E or U. In the equation, H equal to E plus PV, E, P and V all are state functions. Hence, H, that is enthalpy, is also a state function. It means enthalpy does not depend on the path by which that state of the system has been achieved. If delta H denotes change in enthalpy during a process, then delta H will be equal to H2 minus H1, where H2 is final enthalpy of the system and H1 is the initial enthalpy of the system. Substituting all these values in equation 2, we will get delta H equal to E2 plus P2 V2 minus E1 plus P1 V1, that is E2 minus E1 plus P2 V2 minus P1 V1, or we can say that delta H equal to delta E plus delta PV. At constant pressure, delta P will be equal to 0. Hence, this equation comes out to be delta H equal to delta E plus P delta V at constant pressure. As W equal to minus P delta V, hence putting the value of P delta V in this equation, we can get delta H equal to delta E minus W. According to first law of thermodynamics, delta E equal to Q plus W, and equating equation number 3 and equation number 4, we will get delta H equal to Q at constant pressure. It can be denoted as delta H equal to QP. Hence, delta H can be measured by measuring the heat of the system at constant pressure. As enthalpy is a state function, hence change in enthalpy, that is delta H, can be represented as H2 minus H1. Delta H will have a positive sign if final enthalpy is greater than initial enthalpy, that is H2 is greater than H1. When delta H has a positive sign, the process is said to be endothermic process. Delta H will have a negative sign if final enthalpy is less than the initial enthalpy, that is H2 is less than H1. When delta H has a negative sign, the process is said to be exothermic process. For chemical reactions, enthalpy change is measured as enthalpy of products minus enthalpy of reactants. Calorific values of many gaseous fuels are measured at constant volume conditions, that is in closed calorimeters. Hence, volume does not change. As from first law, you know that delta E is equal to Q plus W, where W is minus P delta V. At constant volume, delta V will come out to be 0 and delta E will be equal to Q. Hence, at constant volume, delta E equal to QV. When any fuel is burnt in constant pressure conditions, then the heat exchanged is different from the equation QP equal to delta H. Here, the equation which is to be used is delta H equal to delta E plus P delta V. If gases are involved in the chemical reaction, then volume change is considered the only volume change of gases, because the volume change in liquids or solids is considered negligible as compared to the volume change of gases. Therefore, if N2 is the number of moles of gases in products and N1 is the number of moles of gases in reactants, N2 minus N1 will be equal to delta N, that is change in number of moles in a chemical reaction. By ideal gas equation, we can have P V1 equal to N1 RT and P V2 equal to N2 RT. As delta H is equal to delta E plus P delta V, hence it will come out to be delta E plus delta N into RT. Here delta N is the change in number of moles of gases, that is number of moles of gases in products minus number of moles of gases in reactants, which is equal to N2 minus N1 here. Using this relationship, we can correlate the heat at constant pressure and heat at constant volume. You know that heat at constant pressure is equal to delta H and heat at constant volume is equal to delta E, and we can use the relationship delta H equal to delta E plus P delta V or delta H equal to delta E plus delta N RT. The internal energy, pressure and volume all are state functions, hence enthalpy is also a state function, because enthalpy depends on internal energy, pressure and volume. The absolute value of enthalpy cannot be measured, hence change in enthalpy is measured. Enthalpy change can occur by physical process, that is heat loss to a colder body, or by chemical process, that is heat produced during a chemical reaction. Increase in enthalpy leads to increase in temperature. Hence, heat is absorbed during this process and the process is named as endothermic process. Delta H has a positive sign in endothermic process. Decrease in enthalpy leads to decrease in temperature. Hence, heat is released during decrease in enthalpy. This process is known as exothermic process and delta H has a negative sign in exothermic process. Here are some examples to understand the relationship between delta H and delta E, that is internal energy and change in enthalpy. The first one is the internal energy change in the conversion of 1 mole of the calcite form of calcium carbonate to the aragonite form is plus 0.21 kilojoules. Calculate the enthalpy change when the pressure is 1 bar, given that the densities of solids are 2.71 grams per centimeter cube and 2.93 grams per centimeter cube respectively. We have to use the relationship delta H equal to delta U plus P delta V. Here delta U is given to be equal to plus 0.21 kilojoules per mole or 0.21 into 10 to the power 3 joules per mole. Pressure is given 1 bar, hence it will be equal to 1 into 10 to the power 5 pascals. To calculate delta V, we have to know the volumes of both the forms of calcium carbonate. As 1 mole of calcium carbonate has been taken, hence mass of calcium carbonate is 100 grams. Densities of both the forms are given, hence we can calculate volumes of both the forms. Delta V will be equal to V of aragonite minus V of calcite, which is equal to 100 upon 2.93 minus 100 upon 2.71 centimeter cube per mole of calcium carbonate. This is equal to minus 2.77 centimeter cube or minus 2.77 into 10 to the power minus 6 meter cube. Now, delta H will be equal to 0.21 into 10 to the power 3 minus 1 into 10 to the power 5 multiplied by 2.77 into 10 to the power minus 6. This is equal to 209.72 joules, and converting it to kilojoules, it is equal to 0.20972 kilojoules per mole. We can calculate the change in enthalpy or change in internal energy during physical processes. For example, during boiling of water. There is an example to understand these calculations. Water is boiled under a pressure of 1 atmosphere. When an electric current of 0.5 amperes from a 12 volt supply is passed for 300 seconds through a resistance in thermal contact with it, it is found that 0.789 grams of water is vaporized. Calculate the molar internal energy and enthalpy changes at boiling point, that is 373.15 Kelvin. The vaporization occurs at constant pressure, hence delta H will be equal to work done by the heater. Therefore, delta H will be equal to 0.5 multiplied by 12 multiplied by 300, which is equal to 1800 joules. Converting 1800 joules to kilojoules, we will get 1800 joules equal to 1.8 kilojoules. Molar enthalpy of vaporization will be equal to delta H upon number of moles of water. Number of moles of water will be equal to mass of water divided by molecular mass of water. You know that molecular mass of water is 18. Hence, number of moles of water will be equal to 0.798 divided by 18. Putting all these values, we will get molar enthalpy of vaporization equal to delta H upon number of moles of water equal to 1.8 divided by 0.798 by 18, which is equal to 40.6 kilojoule per mole. Now we have to calculate internal energy change. For this, we will use the relationship delta H equal to delta E plus delta N of gas into RT. Here we have calculated delta H and now we have to calculate delta N. For the equation H2O liquid in equilibrium with H2O gas, delta N gas will be equal to 1 because we are neglecting the volume of liquid water. Therefore, putting all these values in the equation delta H equal to delta U plus delta N gas RT, we will get the value of delta E, that is internal energy. It is equal to 40.6 minus 8.314 into 10 to the power minus 3 multiplied by 373.15, which is equal to 37.5 kilojoule per mole. We can also correlate delta H and delta E when volume change takes place in a liquid. Here is an example to understand that. In an insulated container, 1 mole of a liquid with molar volume 100 ml at 1 bar is placed. Liquid is steeply taken to 100 bar when the volume of liquid decreases by 1 ml. Find delta H and delta U for the process. Here we can calculate delta V by subtracting initial volume from final volume. So, volume of 1 mole of liquid is equal to 100 ml at pressure 1 bar and volume of 1 mole liquid is equal to 99 ml at pressure 100 bar. The process is irreversible as it is steeply changed from 1 bar to 100 bar. Therefore, W is equal to minus P multiplied by delta V, that is minus P V2 minus V1. This is equal to minus 100 multiplied by 99 minus 100. It is equal to 100 bar ml. Now, delta U will be equal to Q plus W. Here Q is equal to 0 as the container is insulated. Now, delta U will be equal to 100 bar ml. Putting these values in the equation delta H equal to delta U plus P delta V, we will get delta H equal to 100 plus 100 multiplied by 99 minus 1 multiplied by 100, which is equal to 9900 bar ml. Let us revise what we have learnt today. First, we discussed some examples related to first law of thermodynamics. First law of thermodynamics can take different special forms in different conditions, that is in cyclic isothermal process, in adiabatic process, in isochoric and in isobaric process. Internal energy and enthalpy are exact differentials and heat and work are inexact differentials. Exact differentials can be integrated between the proper limits, but inexact differentials cannot be integrated between the limits. The heat content of a system at constant pressure is called enthalpy. Therefore, delta H is equal to QP. After that, we derived a relationship between enthalpy change and internal energy of the system. Delta H is equal to delta E plus P delta V, or delta H is equal to delta E plus delta N of gas into RT. Here delta E can also be replaced by delta U. In continuation, in next lecture, we will discuss molar heat capacities.